I was facing issues with recording in the... Okay. So yeah, as you can see from the presentation that we're going to start talking about number theory today. Today we are going to talk about the very basics. We're going to talk about the idea of divisibility, the idea of congruences and such. And then from the next session onwards, we'll look at some applications of congruences in solving some problems, and then also move on to the idea of prime numbers in the next session, right? In this session, we're going to talk about the very basic ideas in number theory. And what is number theory, by the way? So far in our life, we've handled with numbers all our life when we did maths and everything. But how does it work? We divide something by something. We know that this is how it works. But what's the proof for that this holds? Where is that algorithm coming from? And what is the proof of that algorithm? These things, like these ideas that of division, these ideas of factorial. Wherever there is a product, there is a division, by the way, right? So what is the basis of these ideas? All right, where did these things stem from? So we'll talk about these things in number theory, okay, in basic number theory. So first, let's talk about divisibility. You know about the idea of divisibility in the sense that a number dividing another number such that the result is an integer. We've talked about this in one of the previous sessions already when we were discussing induction, I think. Yeah. So when we use this symbol, this symbol, this vertical partition, what it means to say is that the number or integer on the variable or the number or integer, whatever, on the left-hand side divides the integer on the right-hand side such that the result is also an integer, and such that obviously a will never be equal to 0. Since that is a divisor, it will never be equal to 0. That is what it means to say that a divides b and to use this specific symbol. The left-hand side divides the right-hand side such that the result is an integer. So if the result is an integer, that means that there exists some integer c such that we can say that b is equal to ac. See, if the result is an integer, and if we say that result is c, is represented by c, then obviously b will be is equal to ac. Only then b will be b will be divisible by a such that the result is an integer. All right, see, a is here as a factor, so this term is divisible by a, obviously, and we have c here, which is an integer, so the result will always be an integer. Okay, these are some of the terms that we use related to divisibility as well. I've discussed this already. So when we say something like this, it goes to say that a is a factor of b and b is a multiple of a, and that obviously b is divisible by a and a is the divisor of b. Okay, and these examples as well we have discussed when we say that something is not a number does not divide another number such that the result is an integer. We use this symbol. Okay, here don't confuse it with the idea that 5 কে 2 দিয়ে কখনো ডিভাইডই করা যাবে না। 5 কে 2 দিয়ে ডিভাইড করা যাবে কনভেনশনালি, যেটা আমরা জানি যে ডিভাইড করা যাবে where the result is not a whole number basically. All right, so we use this symbol only when the result is a whole number. We use this symbol when the result is, let's say, not a whole number basically. Okay, so based on the definition of divisibility, the basic property of divisibility, it tells us that for some integer a which will never be equal to 0, to say that a divides some integer b and a also divides some integer c such that the result will be integer, we can also say, it is also possible to say that a can divide mb plus nc for some integer m and some integer n. Okay, that is, if a can divide b and if a can also divide c, some integer b and some integer c, then a can also ultimately divide mb plus nc for some integer m and n. Okay, that is the basic property of divisibility. We will use this basic property to prove other things, to prove other properties relevant to congruence, say for example, as well. All right, so remember this property: when a certain number can divide two different integers, then it can also divide the sum of the multiples relevant to those integers. Okay, mb plus nc. Now, to prove this, in order to prove this, I use the idea of divisibility. We'll use this idea. When we say that a can divide b, it goes to say that b is equal to ac for some integer, say. So in that case, can we not say that if a divides b and the result is some integer, A divides B, the result is some integer. Can we not say that if that integer is R, the result, if that integer is R, then B is equal to AR? Can we not say that, guys?
Yes, miss.
Right. Just ekhane je idea ta, same idea is here. Okay. If A divides B, then B is equal to AR for some integer R. Similarly, A also divides C. Can we not say that C is equal to AS for some other integer S? Since A divides C, we can say this as well. Yeah.
No, isn't this the other
Yes,
way
miss.
around? C divided by A.
Sorry? No. A divides C. For this symbol, the one on the left-hand side, the integer on the left-hand side divides the integer on the right-hand side. Here, A is the divisor. C is the one that is being divided. Okay? So if A divides C, tar mane ki C by A gives us some integer as a result. If we say that that integer is S, we can say that C is equal to AS. Does that make sense so far, guys?
Yes, ma'am.
Okay. So in that case, now let's see what we get from MB plus NC. In order to prove this, we have to show that MB plus NC is divisible by A, right? That is, if you divide MB plus NC by A, you will get an integer in the result. That is what we have to prove. Now, MB plus NC, here we have B and C. We know that B is equal to AR for some integer R and C is equal to AS for some integer S. In that case, can we not just replace B and C with these two values respectively, and we get M multiplied with A multiplied by R plus N multiplied with A multiplied by S? Can we not get the sum of these two product terms? So we are replacing B and C with these values respectively. So in that case, CA is in common in these two sum terms. Both of the sum terms have A in common. So if we take A in common, what do we get left? What do we have left with? MR plus NS. Now, MN, both of these are integers, as you can see here. MN, both of these are integers. That was our assumption. So M is an integer. What about R? R is also another integer. B is equal to AR for some integer R. So M and R, both of these are integers. What about the product, MR? Will that be an integer?
Yes.
Okay. Here, N is an integer. S, as you can see here, is also, is also an integer. So the product of N and S, that will also be an integer. What about the sum of these two values then?
Integer.
Integer. So you see, we have A here and here an integer. So can we not say that A can divide this term where the result is an integer? Is this term divisible by A?
Yes, miss.
Yes, it is. A is a factor here. So of course it's divisible by A. And the result will be an integer. Since MR plus NS, as we see, is an integer. So now that we know that, see that this term is equivalent to MB plus NC. So if A can divide this term, where the result is an integer, A can divide this as well, because these two are equivalent. So there you go. That proves that based on the assumption that A can divide B and A can divide C, in that case, A can also divide MB plus NC. Okay. Any questions regarding this proof?
No, miss.
Okay. So understand the process more importantly. See that we utilized the definition of this specific symbol here in terms of this B is equal to S is equal to AS, and then in this expression, and then went ahead to prove that this is an integer, and since A is a factor here, A can divide this entire number. All right. So understand the process, because today I'll ask you about the proof of one property, and in the next session as well, by the next session, I'll ask you maybe to try out the proof. So think about these processes. So in most cases, I see that you guys struggle with proving something on your own. So for that, two things that you need to keep in mind is that where you have to get the destination that you have to get to with the things that you have, and what you have to do in between to get there. Okay. Here, for example, this is the destination that we want to get to, that this number is divisible by A. What we have is that A is divisible by B and A is divisible by C. So basically, we can express it in these terms. Okay. Now, somehow if you can replace B and C with these, we know that A will be there in both terms and we can take A in common and we can get there. Just if A is there in both terms, it means that it can divide this entire term and it can divide this term. All right. So we'll do some more. We'll talk about some more proofs and then I'll ask you to try one out on your own. Very easy one to be a very easy one at that. So the division algorithm. The division algorithm states that for some integer A and for some positive integer D, there exists unique integers Q and R such that A is equal to QD plus R, where R will always be greater than or equal to 0, but will be less than D. So that is R will be within this range, 0 less than equal to R less than D. Okay. Now, this is the algorithm that represents all our divisions that we have done so far. Life jotula division korecho, this is the algorithm that was written in order to be able to do that. Okay. So here Q and R obviously are the quotient and remainder respectively. Q is the quotient, R is the remainder. Excuse me. D is the divisor. Hence, D will always be a positive integer. Since D is a divisor, D will always be a positive integer. A is the number that is being divided. So this algorithm basically talks about the process of dividing some number A with another number D. Okay. Simple division, the way you have done it so far, where the result can be a whole number, the result can be a fraction, the result can be a mix, whatever. Okay. Basically, the result has a quotient and a remainder. So far, the concept that we've discussed here, these ones, here, the remainder is always 0. That means the result is always an integer. Here, we're talking about division as we know it. Okay. If you divide some number A by some number D, where D is a positive integer, you will obviously get a quotient and a remainder. If the result is an integer, the remainder is 0. Otherwise, the remainder is greater than 0. Okay. So this is the algorithm that explains it. A is equal to QD plus R for this range. So for the value of R within this range. So what we'll do is right now we'll prove this algorithm, and for proving that we'll do it in 2 steps, okay, in 2 parts. In the first part, we will prove the existence of this formula, if this formula that represents division along with this definition of R, okay, that is this limit on R. So we'll prove the existence of these 2 expressions, all right? We'll prove basically the coexistence of these 2 expressions based on the definitions relevant to divisibility, okay? Now, what is a quotient by definition? If you divide 6 by 2, what is the quotient?
3.
What is the remainder? 0.
0.
If you divide 5 by 2, what is the quotient? What is the result, first of all? If you divide 5 by 2.
Miss 2. 2 is the quotient.
And what about the result? If you divide 5 by 2?
2.5.
2.5, correct. Now,
The remainder is 0.5.
the remainder is not 0.5.
1.
The remainder is 1. Yeah. See, remember, we get 0.5 by the remainder divided by the divisor, okay? So that is that's what we get from this algorithm basically. But yeah, the quotient, let's talk about the quotient first. Now, you said that the quotient, for example, for 5 divided by 2, the quotient is going to be 2, where the result is 2.5. So what are we doing here? For the division process, the quotient is basically the largest integer that is less than the result or equal to the result in case the result is an integer. Yes? Think about it. The quotient, 2. What is it? 2 is the largest integer that is less than 2.5, right? 2 is the largest integer that is less than 2.5, the result. Yes?
Yes.
Yes.
Yes. So in every division that you will see, you'll see that if the result is an integer, then that is the quotient. That itself is the quotient. And the remainder is 0, obviously. If the result is not an integer, then the quotient is the largest integer, which is less than the result. That is, the quotient is the next integer less than the result. Okay, মানে integer immediate, sorry, resulted immediate আগে যে integerটা আছে, that is the quotient. Now, isn't that the definition of floor function? If we do a divided by d, some number a divided by some positive integer d, in that case, can we not say that the floor function on the result gives us q? Remember the definition of floor function. What was floor function? This is what the floor function does, right? It gives us in the result a number, an integer, which is less than or equal to the value on which we're applying the floor function. All right. So based on the definition of quotient, by definition quotient bolte amra ja bujhi. Can we not say this? And again, don't confuse this with this. Okay, when we use this specific symbol, a vertical partition jeta eta jodi use kori, it means that the number on the left hand side divides the number on the right hand side such that the result is an integer. Here we're talking about normal division. That is, the number on the left hand side is being divided by the number on the right hand side, and the result can be anything. Okay, normal division as we know it. So the quotient, by definition of quotient, can we not say that q will be what we get after applying the floor function on a by d? Can we say that, guys?
Yes, miss.
Okay, if that makes sense, in that case, when will q be equal to a by d? Can you tell me? Will q ever be equal to a by d?
No, miss.
Q will never be equal to a by d. What if your a is 6 and d is 3?
Yeah, then it will be.
So can you say that q will never be equal to a by d?
No, miss.
So basically q will sometimes be equal to a by d. When is it? When will q be equal to a by d?
When q itself is this, when we are applying
When the result basically is an integer. Yeah?
Yes, miss.
When the result is an integer, quotient will be equal to a by d. So that's one possibility, that q might be equal to a by d. Q will not be equal to a by d when the result is not an integer. Okay, in that case, will q be greater than a by d or less than a by d? Tell me that. Will the quotient ever be greater than the result?
No,
No, miss. Greater.
No, it won't. So q will either be equal to a by d only when the result is an integer, and if the result is not an integer, q will be less than a by d. Correct? That is what we understand by the definition of the quotient. Yes?
Yes, miss.
Okay.
Yes,
In
miss.
that case, we can say that q will be less than or equal to a by d always. Also, a by d, the result of a by d will be less than q plus 1. Why? Because a by d will be equal to q when a by d is an integer. The result of a by d is, if it's an integer, it will be equal to q. In that case, obviously it will be less than q plus 1. If it's equal to q, it will definitely be less than q plus 1. What is the other possibility? The other possibility is that a by d is not an integer. A by d, the result is not an integer. In that case, what is q? The q is the largest integer that is less than this result. So basically, the next integer to the left of it on the number line. Okay. So in that case, q plus 1 will always be greater than a by d. All right. Whether a by d is an integer or not, q plus 1 will always be greater than a by d. So we can say that a by d is less than q plus 1. So we can say this based on the definition of quotient. We can say something like this, that q is less than equal to a by d, and a by d is less than q plus 1. Can we not?
Miss, এখানে q plus 1 কেন বলা লাগবে? Like we can already say that q is less than equals to a by d.
Yeah, there is a point to that. You see that. There's a reason to that. Why? Because we want to get here, okay? We want to get here from this definition. Remember, in the first part, we are proving the existence of this equation and this expression, all right? These two equations, basically, the existence of this equation and this equation. We are going to prove that these two equations do exist based on the concept of division and quotient and these things. Amra division bolte ja bujhi, quotient, remainder, eshob jinish bolte ja bujhi, based on that, this equation and this equation, these two do indeed exist and they coexist together. This is what we'll prove first. So in order to get here, see, x side a, do side a, you have to, basically you have three values here. Okay, you'll see that we'll get there from this definition. So basically you need a lower limit and an upper limit, both of them. So that's why we are using q plus 1, the idea of q plus 1 as well. However, the fact that this holds based on the definition of quotient in division, this equation holds. Does that make sense? That a by d will always be less than q plus 1 and q will always be less than equal to a by d. Does that make sense?
Yes, miss.
Okay. All right. In that case, what we will do is we will multiply all sides with d. All right. First, we'll multiply all sides with d. So here we'll get q multiplied with d. So we get qd. Here a by d multiplied with d gives us a. So we get e here. And here we get q plus 1 multiplied with d. So we get this equation basically. Qd less than equal to a less than q plus 1 into d. All sides here we multiply d simply. All right. So in that case, this is the expression we have from there, right? Qd less than equal to a less than qd plus d, right? So far it's pretty straightforward, right? Simply on all sides we have multiplied d and we get qd less than equal to a less than qd plus d. Then next what we will do is we will subtract qd from the entire equation. Okay, so qd minus qd gives us 0, a minus qd gives us a minus qd plus d minus qd gives us what? D. Now guys, is a an integer? Is a an
Yes,
integer?
miss.
Yes.
Very good. Is the quotient always going to be an integer?
Yes, miss.
That's correct. Is the divisor an integer? D. Is d an integer?
Yes, ma'am.
Yeah, that's an integer as well. So qd will also be an integer, obviously. And a minus qd then, will this be an integer always?
Yes, miss.
Okay. So if a minus qd is going to be an integer always, let's say we use some variable to represent this integer. Okay. Let's forget about remainder or anything. Just use some variable r. A minus qd will always be an integer. A integer result a minus qd is equal to some integer. Some integer ta will use r to represent this integer. Okay. So we'll use r to represent this integer. Okay. So in that case, what do we get here? A minus qd, if we represent it with r, we get 0 less than equal to r less than d for some integer r. Okay. So we get this 0 less than equal to r less than d. Also, r if is equal to a minus d. If we say r is equal to a minus d, sorry, a minus qd. If we say that r is equal to a minus qd, based on which basically we get this equation. If we say r is equal to a minus qd, take qd on the left hand side, what do we get? A is equal to qd plus r. All right. This is the very equation that represents division itself. All right. R equals to k minus d, a is equal to qd plus r for some integer r, for some integer q, all right, where r will be within this range. Okay. So see here, that was the point of q plus 1. That was the point of dividing the whole thing with d and subtracting qd. All right. So you have to, again, remember what is our destination. So here, so far, amar kache eta ache. We have to keep this in our mind. Okay. A, qd, all of these things are here. I have to bring in r. A minus qd. Okay. So a minus qd ante hobe, where a, qd, all of these are already integers. So a minus qd will also be an integer. So we have to get there. That was our goal. J minus qd, we have to get to a minus qd. That is the reason we divided d, sorry, we multiplied d all throughout and then subtracted qd from the entire equation. All right. That is the reason we did that. And also, at the same time, we wanted to get this equation. So that's why we had a lower limit and an upper limit from which we could possibly get d as the upper limit. Okay. So yeah, as you can see here, we started from the basic definition of a quotient in division. We know about the definition of quotient. We know about division, how it's done usually. We started from that. From that division, we got this. We got this equation. And from this equation, we got this for some integer r, which is equivalent to a minus qd for some integer r. So from this as well, if r is that some integer which represents a minus qd, we can also say that a is equal to qd plus r. See, so far, for some integer r, so r is an integer, q is an integer. We already know that by definition. All right, a and d, they are integers because we are dividing two integers with each other. All right, and for this equation holds true as well. That is, these two equations coexist together. Okay. So we started with the definition and proved it that this equation does exist for some integer q, some integer r, some integer a, some integer d. All right, where r will always be within this range. So here basically you are proving the existence of these two equations and these two coexisting together. Okay, so that proves that this equation does represent the idea of division. Okay, this equation can be used in order to represent the division algorithm where q and r are some integers and r will always be greater than or equal to 0 but less than d. Okay, any questions so far?
Miss, last line a equals to qd plus r. Like এইটা কিভাবে আসলো?
A equals to qd plus r just because a minus qd তো আছে, তাই না? Minus qd যদি একটা integer হয়, if this is an integer, we can use some integer r to represent that. A minus qd তো একটা integer হবে, 5, 6, whatever. একটা one integer, it will be one integer. That integer is being represented by r. So if r is representing the integer a minus qd, we also can translate this equation or transform this equation in terms of a and say that a is equal to qd plus r. Take qd on the left hand side. What do you get? A is equal to qd plus r. Okay.
Yes.
So as simple as that. Basically, আমরা যেটা বলছি যে if this is true, based on the definition of coefficient, we get this. If we are using indeed the idea of division as we know it and the idea of quotient, then this is what we get. And from here, this is what we get. That for some integer r, which is equal to a minus qd, this range will always hold true. This equation will always hold true. 0 less than or equal to r less than 2. That's what we get here. And at the same time, a is equal to qd plus r. That is, these two equations go hand in hand. And this can indeed represent the idea of division because we got here from the idea of division as itself. Okay. Is that clear?
Yes, miss.
Okay. All right. Now that we've proved that these equations do exist and they can represent division, the division algorithm, now we'll go on to prove one small detail that's left. It also says in the algorithm that q and r will be unique. There exist unique integers qr such that a is equal to qd plus r. What it basically means is that for the same integer a, that is if you don't change a, and for the same integer d, that is if you don't change d, if you fix a and fix d, for the same a and same d, there will be only one q and only one r. We know this is true. We know this is true from our entire life of doing divisions. Okay, if you give me any integer, all right, give me any integer.
Miss 5,
5. Give me another integer.
15.
15. Okay. So let's say we have 15 and 5 for AD. Okay. So let's say we are trying to divide 15 by 5. So D is equal to 15, A is equal to 5. If we do not change D value, A is equal to 15, D is equal to 5. If we do not change these values, 15 or 5 ke jodi change na kori, for these two same numbers, A is equal to 15, D is equal to 5. If you try to divide A by D, what is the quotient you will get and what is the remainder? Quotient ki hobe first of all if you divide 15 by 5?
3,
What is the remainder?
0.
Is it possible to get any other quotient other than 3? 3 chara onno kono quotient pawa ki possible?
No.
Miss.
No. Is it possible to get any other remainder other than 0?
No.
No. And that holds true for any such examples. Okay. If you fix A and fix D, for the same A and same D, basically, Q and R will always be unique. There will be only a unique quotient and a unique remainder. Okay. For the same number A and the same number D. Okay. If you divide A by D. That is something that we know to be true. However, what is the proof of that? Based on what proof did this algorithm come to being? Kishet theke, mane what is the source of this idea? Amra jani on application in pen and paper we see that examples say okay this never happens. But if you demonstrate something by example, is that a solid proof? No, because the world of number is infinite. Okay, so we in number theory this is what we do. We go to the basics, that is how did this idea come to being? What is the proof of these things? আমি সারা জীবন use করেছি, I have handled numbers my whole life, but based on what? All right, so that is the basis of it. Number theory discusses these things. Okay, so now Q and R, in order to prove that they are going to be unique, we know that the quotient and remainder will be unique based on our experience with division, but we have to prove it nonetheless with logic. Okay, not just by examples. So Q and R will be unique. In order to prove that, we'll use proof by contradiction. What do we do in proof by contradiction, guys? You've done proof by contradiction, come on. গতকালকে তো আমি একটা চেক করতেছিলাম মিড টার্মে প্রুফ। অলরাইট, nonetheless, proof by contradiction এ what do? We যেটা আমাদেরকে প্রুফ করতে হবে, we assume the opposite. We have to prove that Q and R are unique. The quotient and the remainder will always be unique. That is what we have to prove. We will start by assuming the opposite, and from there, if we can derive a contradiction, what does it mean? That the opposite statement can never be true. If that leads to a contradiction, that leads to a contradiction, it means that that statement can never be true. If that is the case, then the original statement that we had to prove must be true. That is, we have to prove that Q and R are unique. So we will first start by assuming that what is the other possibility? If they are not unique, if I have to prove that they are not unique, if you're saying that they are not unique, then the only other possibility is that exactly that Q and R are not unique. They're for the same A and the same D, basically there is some other quotient and some other remainder. For the same A and the same D, there's some other quotient Q1 and some other remainder R1, let's say. That is the only other possibility. Then from there we'll have to get to a certain point where we'll see that okay, this is a contradiction. It must mean that some other quotient and some other remainder does not exist. That is, Q1 and Q are the same number, R1 and R are the same number. That is, Q and R are unique. Okay, that is what we will do. So if they are not unique, then it means there must exist some other integer Q1, and some other integer R1 for the same A and D, such that A is equal to Q1D plus R1. Correct? If there's some other Q1 and some other R1, we can also represent the division in this way, right? Guys?
Yes, miss.
Yes, miss.
Where 0 less than equal to R1 less than D. Okay? Similarly, just like before. We've already proved the existence of these two equations, right? So we can use that. We've already proved the existence. So যেহেতু ওটা proof করেছি, we can use this two. And if A is being divided by D and we get Q1 and R1, some two other set of integers, then we can say these things. Now, R is less than D. R is some integer which will always be less than D. R is some positive integer at that. Remainder is always positive, yeah? So, sorry, R is a non-negative integer. Sorry, non-negative. Remainder is always non-negative. So, R will always be less than D. R is greater than equal to 0 and R will always be less than D. R1 will also be always less than D. If you have two sets of remainders, we can use this algorithm twice in this way, and in both cases, by definition, the remainder R1 will be less than the divisor, and it's going to be a non-negative integer. In that case, can we not say that the difference between R and R1, the modulus of that difference will always be less than D? If
Yes,
it's
yes.
negative, it will obviously be less than D. If it's negative, it will be less than D, obviously. Because D is a positive number. Remember, D is a positive integer. If it's negative, it's obviously going to be less than D. But just to avoid confusion, even for positive cases, so we take the modulus. The difference between the two. R to individually is less than D. R to ekai diye theke choto. R1 also alone on its own is less than D. So the difference between the two will be smaller. The difference between R and R1 will be smaller. Also remember that R is non-negative, so the difference will obviously be smaller. And we are taking the modulus. Even then, it will always be less than D, right? Now, if that part is clear to you, in that case, A is equal to QD plus R. And for the same integers A and D, we are saying that A is equal to Q1 D plus R1 for a different set of quotient and remainder. A is equal to Q1 D plus R1. So the left-hand side is the same. Can we not say that QD plus R is equal to Q1D plus R1? Can we not say this?
Yes.
Yes,
In
ma'am.
that case, if we transfer the R1 to the left-hand side, we get R minus R1, and then QD to the right-hand side, we get Q1D minus QD, where we get Q1 minus Q into D. Okay? So basically, then if we take the modulus on both sides, since this is an equality, we are allowed to take modulus as long as we take it for all terms, right? So modulus on all of them, R minus R1 mod is equal to R1 minus R1 modulus is equal to Q1 minus Q1 modulus and D modulus. Now, D, remember, is always going to be a positive integer, right? D is always going to be a positive integer. Is there any point in taking the modulus of D? Modulus of D will always be equal to D, right?
Yes, miss.
Yes.
Okay. Now that we know this, D will always be positive, and so we can represent it this way. So we have this in our hands, right? This equation. The modulus of R minus R1 is equal to the modulus of Q minus Q1 multiplied with D. Or in other terms, D is equal to the difference between R1 as R1 and the modulus of it divided by the modulus on the difference of Q1 and Q. All right. Now remember that D is a positive integer. So D, this one will always be a positive integer. Also remember that the difference between R minus R1 and the modulus taken on it is less than D. That is, the numerator here is going to be less than D. But D is the result, that is the result of this division. The result of this division is a positive integer where the numerator, the one that we are dividing, the term that we are dividing is less than D. How will it be possible? This will be possible only and only when this, the denominator, the one that is the divisor is a fraction. Only when the divisor is less than 1, is between 0 and 1, right? Does it make sense?
Yes, miss.
So,
Miss, confused it too.
okay, give me any number for D, any integer for D. D will be a positive integer, so keep that in mind. So give me any value for D.
7.
7. Give me a different value for R minus R1 modulus.
2.
2 divided by what number will give you 7? তুমি 7 কিভাবে পাবা? If the numerator is 2, if you're trying to divide 2 and you're trying to get 7 in the result, see on the left hand side, what do we have? 7. If you want to get 7, in order to divide 2, the only way you can get there possibly is if you have a fraction in the bottom, right?
Yes, miss.
The only way to get there is if you have a fraction in the bottom. That is, if the divisor is less than 1, between 0 and 1. Now, does it make sense?
Yes, miss.
This will always be true because we know that D is a positive integer. That is one of the foundational, that is one of the basis of the algorithm. Okay, D is a positive integer. Since D is a positive integer and this term is always going to be less than D, the only way you can get D in the result of this division is if this divisor is less than 1. Okay, that is, it's a fraction. Say, for example, if you have D is equal to 5, and let's say this is, D is equal to 10. If say D is equal to 10, if the divisor is 10 and the difference between the two remainders, the modulus, if there are two different remainders indeed, let's say this is 5. So D is equal to 5 divided by what? How will you get to 10 when the numerator is 5? Only and only if the denominator or the divisor is what?
0.5.
0.5, exactly. So always in this scenario, Q1 minus Q, in order for this equation to hold, Q1 minus Q, the modulus of Q1 minus Q will have to be less than 1. Okay, will have to be less than 1. That is a fraction between 0 and 1. Okay. So based on this equation, we can say that the modulus on Q1 minus Q will be less than 1. Okay. Based on this equation and the fact that the modulus on R minus R1 is less than D. Okay. Now, the problem with this lies with the basis of the algorithm. The quotient. What type of number is the quotient? Tell me. In a division, the quotient that you get, what type of number will it be? Will the quotient ever be anything other than an integer?
No, miss.
That's correct. The quotient Q will always be an integer. Q will always be an integer. So in that case, quotient Q and quotient Q1, both of them are integer. If you try to find the difference between two integers, will you ever get a fraction? Due to integer difference, will it ever give you a fraction?
No, miss.
No, it won't. So you see, in order for this equation to hold, the difference between Q1 and Q has to be a fraction, which is not possible because Q1 and Q, we know that they're integers. We established that quotient, we know by definition that a quotient is an integer. So Q1 and Q are integers. The difference between the two will never be a fraction. However, if the difference between the two is not a fraction, then this equation does not hold. That is, this equation does not hold. That means that we have a contradiction in our hands. The opposite idea that Q and R are not unique gives us a contradiction, gives us an impossible scenario. Okay, so it must mean that Q1 minus Q is not a fraction. Also, that the result is 0. That is, Q1 and Q, they are the same numbers. The conclusion must be that Q1 and Q are the same numbers and R1 and R are the different numbers. But assuming that they are not unique, that is, there is some other quotient or some other remainder, we see that we are arriving at a contradiction. It must mean that the quotient and the remainder for the same A and the same D will be unique. Okay. That is, Q1 and Q basically are the same number. R1 and R is the same number. Okay. Any questions regarding the algorithm and the proof? Okay. So I'm assuming that it's clear with everyone. All right. So the idea of a quotient and a remainder, we already know what a quotient is and a remainder is. Okay. The way we express it in the way we will express it in the scope of our course, that is the scope of the concepts that we are studying in number theory, we use the diff function and the mod function. The diff function gives us the quotient and the mod function gives us the remainder. We already know this. I'm sure you have used the diff and mod functions in programming as well. So yeah, it's the same diff function and the mod function. So for some integer A and some integer D, where D is obviously going to be a positive integer, A div D gives us the quotient. A mod D gives us the remainder of what? Of the division between A and D. If you try to divide the number A by the number D, where D is always going to be a positive integer, in that case, the quotient of that division, we will get that from the diff function. A div D always gives us the quotient and the quotient only. And the remainder of that division, we'll get it by the mod function. A mod D always gives us the remainder. Okay. All right. So diff function and mod function, we use them for these purposes. Now, basically, by example, let's say if we have some number 101 and some number 11, and if you try to divide 101 by 11, what do you get? As a quotient, 101 ke 11 they divide korle, what do you get? 9 point something something something, right? So basically, what is the quotient? 101 divided by 11.
9.
9, exactly. The result is 9 point something something something. So the quotient will obviously be 9, floor function on that. And what is the remainder? 11 nines are 99. So what do you get in the difference?
2.
2. So the remainder is 2. So this process, this is separated into 2 parts. For ease of use or ease of expressing other ideas, this process is separated into 2 parts. Also, in programming as well, in problem solving, you must have seen that the div and mod function is used in solving a lot of problems. All right. So that is the purpose of dividing this up. So the diff function, by default, we assume the diff function, what it will do is it will give us the quotient of this division. As you have just mentioned that the quotient is 9, so you get 9 in the result of the diff function. And the mod function, you said that the remainder is 2, so the mod function between these two numbers will give us 2. All right. Similarly, for any other number either. Say if the numbers are minus 11 and 3, then the division of these two gives us the coefficient minus 4. So the diff function, which always extracts the coefficient, gives us minus 1. The mod function gives us the remainder, which is 1. Okay. Just the idea of quotient and remainder, which is used in a lot of concepts in number theory, and even apart from that, you must have seen the use of these things in problem solving anyway. Okay. Now we'll talk about the concept of congruence. All right. So what is congruence? What do we mean by congruence? I'm sure that this is a new term for most of you guys, at least. So for some integer a, b, m, for some integers a, b, and m, where m will always be a positive integer, that is, m will never be equal to 0. For some integers a, b, and m, where m will always be a positive integers, to say that a is congruent to b mod m, we write it this way. When you see something like this symbol, don't get it confused with equivalence. All right, this symbol, because I got that from the last session in the other section. So don't get this confused by equivalence. This has nothing to do with equivalence. This is congruence. All right, this is congruence, a completely different idea. So how do we represent the fact that a is congruent to b mod m? This is how we represent it. This is the symbol. These 3 bars together, these horizontal bars together, represent congruence. It says that a is congruent with b, or congruent to a is congruent to b mod m. Okay, and what does that mean? It means to say basically that the number and the integer, the positive integer m, can divide a minus b. All right. To say that a is congruent to b mod m, it means to say that m can divide a minus b. Okay. And when we say divide, see, we are using the vertical partition, this symbol here. M divides a minus b such that the result will be what, guys? When we use this symbol, what does it mean?
This result will be an integer.
Always be an integer, exactly. It means that a minus b is divisible by m, and when we say divisible, for this case, we are going to say that the result will always be an integer. The remainder will always be 0. Okay. So to say that a is congruent with b mod m just means to say that m, the positive integer m, can divide a minus b such that the result is an integer. For example, 17, the number 17 is congruent with b mod, this number 17 is congruent with 5 mod 6. That is true. This is true. How can we say that? It's true. A minus b. What is that? 17 minus 5. What is 17 minus 5, guys?
12.
12. What is m here? 6. Can 6 divide 12 such that the result is an integer?
Yes, miss.
Yes, it can.
Yes.
So that's why we can say that 17 is congruent with 5 mod 6. However, 24 is not congruent with 14 mod 6. Can you guys say why?
Means because the result is not an integer.
The result of what?
Miss 24 minus 14.
24. The result of 24 minus 14 is 10.
No, miss.
4 minus 14 divided by 6 is not an integer.
Yeah. I know that that's where you were heading. I was just messing with you. Yeah, that's correct. So, yeah, this is not, 24 is not congruent. 24 is not congruent with 14 mod 6 because, just like you said, 24 minus 14 is 10. And if you divide 10 by 6, the result is not an integer. That is, 24 minus 14 is not divisible by 6 such that the result will be an integer. Okay. So that is the idea of congruence. Any questions regarding the definition of congruence?
No, miss.
Okay. So why are we talking about this thing at all? Because you will see later on that we are going to use the concept of congruence to prove a lot of things, okay? Not the concept of congruence for that matter. When we know the idea of congruence, there are some properties that are there related to congruence. If you understand what it means for some integer to be congruent to some integer, not some other integer, some other positive integer, based on this definition, there are some properties. We'll see 5 properties to be exact. And those properties can be used in order to prove other properties or other things. So far, that is like I've mentioned previously already. So far throughout your entire life, you have done so many divisions. But what is the basis of all those things? Everywhere there's a product, there's also division. So where do these things come from? Say, for example, the idea of a factorial is what? The product of a certain type of numbers, all right? So all of these things, they stem from some idea. So এই জিনিসগুলো, এই idea গুলোতে যে আসি, all of these things have been proved. The idea of a factorial, there is a proof for that. Every single concept that you have used so far, there is a proof for that. What is the basis of these things? We discuss these things in number theory. Everything related to number, okay? We can't do everything because of limited time. At least the very basics, we'll discuss those things, okay? So congruence, the idea of congruence and the properties of congruence are often used to prove other things. Say, also to come up with new algorithms, maybe you can use the idea of congruence. So as you've seen in the division algorithm, we've used what? Ideas that we already were familiar with. Floor function. See, something that you studied so far back has been used here in division algorithm to represent a definition, okay? So প্রত্যেকটা জিনিস, everything that you're learning is used in the proof of some other thing. So basically, why? Over and over again, I get the question that what is the point of doing all these things? What is the application? The application is in data structures and algorithm. Okay, data structures and algorithm. Understanding the algorithm, the existing algorithm, for that as well, you need some of the concepts that you learn in discrete mathematics. Also, more importantly, evaluating the efficiency of a certain algorithm. একটা algorithm কতটুকু efficient, এটার জন্য you need discrete mathematics, all right? And আরেকটা জিনিস যেটা, coming up with new algorithms, as you have seen so far, must have seen so far in discrete mathematics. In discrete mathematics, as you must have seen so far, always we prove things that we are already familiar with. Why? So that you get the idea that okay, মানে আমি for example division algorithm যে proof করলাম, an algorithm মানে যেটা হচ্ছে কি আমরা সবসময় ইউজ করেছি, এটা প্রুফ করা হয়েছে, so that when you hopefully inshallah someday come up with a new algorithm, you know how to prove that, okay? So in discrete mathematics, that is what we do, all right? We try to establish the basis of the process of proving an algorithm, so that when you come up with a new algorithm, you can prove it. Also, existing algorithm, the way the fact that the existing algorithm they make sense, you can prove that using discrete mathematics. Also, in order to understand them, you can use discrete mathematics and to find out the efficiency of them. And same goes in data structures, all right? So these are the reasons we are talking about these very basic ideas, congruences, divisibility, these things, okay? This is in number theory, we are doing that so far we've just looked at applications, all right, operations, but how do they work? What is the basis of those? What is the proof of that? So that if you understand how these things work, how something is proved, maybe someday when you try to come up with a new algorithm, you can utilize this idea. So this is the basis of it, the foundation, okay? And then you build on top of that in data structure and algorithm. You learn more about how to come up with new algorithms, how to calculate the efficiency of an algorithm. You study these things. What is data structure? How to define a data structure. You study these things further on data structure and algorithm. So discrete mathematics, on top of that, you build some more on data structure and algorithm, and then you apply those concepts when you go into, let's say, something like ML, okay? At the very core of ML are these ideas, okay? All right. So now, if you understand what it means by congruence, some properties of congruences, all right? For integers a, b, c, and m. For integers a, b, c, and m, where m is a positive integer, m will always be a positive integer. we can say that A is congruent with A mod M. Always A will be congruent with A mod M. And that makes sense, right? It makes sense. Obviously, A will be congruent with A mod M. What can we say about A is congruent? What can we say about this equation based on the definition of congruence, guys? What does it mean to say this? You know the definition of congruence now. What does it mean to say this?
It's A minus B will be divided by M.
A minus B will be divisible by M such that the result is an integer. What is A here? A. What is B here? A. So basically, this tells us that A minus A is divisible by M such that the result is an integer. What is A minus A? 0. If you divide 0 by M, what do you get? 0, an integer. Okay? So obviously, this will always be true. Okay? So similarly, think about the second property. First of all, what is the second property saying? That is A and B are interchangeable in this congruence. Okay? So if A is congruent with B mod M, B is also congruent with A mod M. Okay? And why does it make sense? Because, first of all, tell me, what does this mean? A congruent with B mod M. Etar mane ki? Again, tell me.
Means the difference between A and B is divisible by M.
Okay, very good. If A minus B is divisible by M and you get an integer in the result, A minus B ke divide korte parle, B minus A ke divide korte parbe na? Think about it.
Yes,
If
ma'am.
M can divide A minus B, M can also divide B minus A. And that is what this is saying, is it not? That B minus A is also divisible by M. Positive na negative hobe result, eta niye to amar kono problem nai. Result positive ho, negative ho, that's not our concern. Our concern is the result has to be an integer. Okay? And A minus B, if M can divide A minus B and the result is an integer, M can also divide B minus A and the result will still be an integer. Positive, negative, kina, that's not our concern. Okay? So this property also obviously makes sense. And then we have the third property, which tells us that if A is congruent to B mod M and B is congruent to C mod M, then A is congruent to C mod M. Try out this proof. Think about it. First, what is the hypothesis? Hypothesis hoche giye A is congruent to B mod M and B is congruent to C mod M. You are allowed to assume that these two are true. Based on that assumption, you have to prove that this is also true, that you can derive this from these two assumptions. All right? So you have to do that. Try it out, you guys. First, I'll give you a hint. First, think about this part, what it means. What does it mean? It means that A minus B is divisible by M. That's what it means, right? And similarly, what does this mean, guys?
B minus C is divisible by M.
Okay, very good. Now, think about how you can get here from these two, all right? Also remember that you're allowed to use the properties that you have already proved, or the properties basically we have discussed already, all right? You can use those properties. You don't even have to go far. You don't even have to go further from this session. In lecture session, আমরা already একটা property discuss করেছি যেটা use করে এটা proof করা possible. Okay? Basic property of divisibility. The basic property of divisibility tells us what? That if A can divide B, and at the same time, if A can divide C, A can also divide MB plus NC. All right? That is the summation of the product terms where you have B and C. Okay. So basically, if A can divide B and A can divide C, A can also divide some form of summation of the two numbers B and C. Here, MB plus NC. Okay. So use that idea and tell me now, how can we get here from these two assumptions? From these two assumptions.
Miss, we will use A minus B is divisible by M, then ওখান থেকে একটা equation পাবো যে
Very good. Yes, that's correct. Go ahead. You don't have to tell me the equation, but you get the idea. Yes. And then what?
then Miss B and C, Miss B minus C divided by M করে আরেকটা equation পাবো, then
Yes, correct.
combine করে আমার common আসবে একটা, then
ওই দুটো থেকে
হ্যাঁ একটা common
ওই
আসবে।
দুটো মানে কমন কিভাবে নিবা? মানে এই দুটো ইকুয়েশন তো আলাদা আলাদা. How will you combine them? What did we do here? Remember, what did we do here? It's a summation, right? Summation.
Yes,
We're
miss.
proving that the summation is also divisible. That's what you will do here as well. Aina, think about it. Based on the basic property of divisibility, if a minus b is divisible by m such that the result is an integer, and b minus c is also divisible by m such that the result is integer, can we not say that the sum is also divisible by m?
Yes,
We are
miss.
not saying exactly what we will get in the result, but we are saying that the sum should be divisible by m as well, and the result will still be an integer based on the basic property of divisibility, right? So a minus b plus b minus c should be divisible by m, all right? So a minus b plus b minus c korle ki pawa jay? A
plus
minus b,
a minus.
a minus c, exactly. The b's get cancelled out, a minus c. So what does it say? That a minus c is divisible by m. Is that not exactly what this is saying?
Yes, miss.
There you go. As simple as that. All right. So yeah, the reason I'm doing these practices is because I get a lot of complaints regarding how to get to a certain proof. So yeah, I mean, even here, see, first, where do we have to get to? A minus c is divisible by m. এটা আমাদেরকে প্রুফ করতে হবে। a minus c টার্মটা কিভাবে পাবো? এই দুটাকে সাম করে। Wait, I can actually do that because based on the basic property of divisibility, if these two, a minus b and b minus c, are divisible, then the sum will also be divisible. From there, we can get here, okay? So in order to prove things, the two important things are, you have to remember what are the concepts that I have learned so far? What are the things that I can use? কোন জিনিসগুলো আমি use করতে পারবো? Everything that you've learned so far, you can use all of those concepts. All right? Any other identity you can utilize in order to prove a new identity. Okay? So use those and then also think about where do we need to get and which specific idea we are going to use to get there. Here, for example, we use the basic property of divisibility. All right? Similarly, you can do that for some other proof. We'll try to see that for one of the proofs here, okay? And the other one, I'll leave it for you. You think about it, take your time to think about it and get back to me. It's easier actually, the one that you have to do. Okay, first, two more properties of congruence. These are the three properties. These are one of the first three properties, the very basic three properties. You will see that we can use these three properties to prove other things as well. To solve problems, to prove other things, you can use any of these three properties. Also, you can use any of these two properties relating to congruence as well. Now, what do these properties say? For some integer a, b, c, d, and m, where m will always be positive, m will never be equal to 0, m will always be positive. For these 5 integers, if a is congruent to b mod m and c is congruent to d mod m, we can also say that a plus c is congruent to b plus d mod m, ac is congruent to bd mod m. All right. So basically, if a is congruent to b mod m and c is congruent to b d mod m, then left hand side je duto ache, sum them up, you get a plus c. Right hand side b and d, sum them up. So a plus c is congruent with b plus d mod m. AC, the product of the left hand side AC is congruent with BD mod m. Okay, so this is just for remembering, all right, that these two properties, এই property গুলো just মনে রাখার জন্য আমি এভাবে বললাম। But what is the proof? মানে কিসের বেসিসে বলছি যে if A is congruent to B mod m and C is congruent to D mod m, এই দুটাকে sum করলে then that number will be congruent with B plus D mod m as well. কিসের বেসিসে বলছি? Based on what we are saying that. We will prove the second property here right now, and I will ask you guys to think about the first property, okay? So the second property, what is it? That AC, the product of AC, the product of A and C, AC is congruent to the product of B and D, the right hand side B, D mod m, okay? AC is congruent to BD mod m, okay? So we're not actually multiplying these two expressions. It's not like that. Please don't get confused. I'm just saying this in terms of, in this manner, just so that later on you remember, okay, congruence একটা property আছে এরকম কিছু. But in no way are we multiplying these two expressions. No, there is a mod. It doesn't work like that. It's not that simple, okay? So, and as you can see, the mod m part doesn't change. So it's not that simple. So let's go ahead and try to prove this. AC is congruent with BD mod m. Now, in order to do that, in order to prove this, first of all, let's see what this expression means. AC congruent with BD mod M. What does it mean to say that, guys? Etar mane ki? Congruence এর definition অনুযায়ী
Miss AC minus BD will be divisible by M.
M. Yes, and the result will be an integer. Yes, that's correct. Now, we have to prove that AC minus BD is indeed divisible by M. That is what we have to prove. Now, before that, what does this expression mean? Similarly, eta ki bole? A minus B is divisible by M. What does this tell us? Guys?
C minus B divisible by M will give us an integer.
And yeah, that A minus B is divisible by M and C minus D is divisible by M, and in both cases we'll get an integer. Yeah, that's correct. Now, A jinishta we are allowed to assume. These two things we are allowed to assume. We have to get to the destination, which is proving that this is divisible by M. We have to get there using this assumption, these assumptions. Okay. So, amader kache ache A minus B, amader kache ache C minus D. Okay. A minus B or C minus D. We know that A minus B and C minus D are divisible by M. How can we get from here to A minus B and C minus D? A minus B and C minus D এখান থেকে কিভাবে পাবো? AC minus BD থেকে directly তো পাওয়া যাচ্ছে না. We have AC here. In order to get A minus B, we would need some BC. In order to get C minus D from here, we'd need another BC. So basically, that's why we are doing minus BC plus BC. First of all, before that, am I allowed to do this, guys? Minus BC plus BC. এই equation এ বসালে
Yes, miss. দুইটার সাথে যদি আমরা BC minus করে দিই তাহলে তো ইকুয়েশন এটাই আসছে।
yeah, so it's the same equation basically, right? Minus BC plus BC. If the BC's gets cancelled out, you can get back to the original equation. As long as we can go back, we can do any algebraic manipulation. So minus BC plus BC is something that we are allowed to do. All right. So why? That we understand. Fine, that এই জিনিসটা করা যাচ্ছে, but why are we doing this? That is the more important part in my opinion. যে বুঝাটা যে কেন করছি, so that you can replicate this when you have to prove something. Why are we doing this? Because আমাদের গোল হচ্ছে গিয়ে A minus B, এই টার্মটা আনা, because we know that A minus B is divisible. আমাদের গোল হচ্ছে গিয়ে C minus D, এই টার্মটা আনা. We know that C minus D is divisible. We want to get there. That's why আমরা BC, we brought it here. Here now, if you take C in common, you get A minus D from these two terms, these two sum terms, right? And from here again, if you take B in common, you get C minus D. Now we have A minus B and C minus D. Now, tell me, A minus B, already we have that in assumption that A minus B is divisible by M. So if you divide A minus B by M, what will you get? You'll get an integer here. What about C? Is C an integer? Yes. It's an
Yes,
integer.
miss.
C is an integer. C is an integer. If you divide A minus B by M, you get an integer. So C multiplied with the result, which is an integer, gives you what? An integer here. This sum term, that is, will be an integer. Similarly, this sum term, what about this sum term? What will it be? Can we say that it will always be an integer? Can we say that this specific term is always going to be an integer? Guys?
Yes, miss.
Yes, we can say that. Because C minus D, if you divide C minus D by M, you get an integer, and that integer multiplied with B, which is already an integer, will give you an integer. So integer here, the sum of two integers also give us integer. So basically what I'm trying to say is that if you divide this entire expression by M, the result is an integer. If you divide this entire expression by M, the result is an integer, right? Is that correct?
Yes, miss.
Yes, miss.
If that is correct, in that case, this expression is the same expression as AC minus BD, is it not? This is equal to AC minus BD. So if M can divide this, and the result is an integer, M can also divide AC minus BD, right? So basically, we can say that M can divide AC minus BD, that is, AC minus BD is congruent. Sorry, AC is congruent to BD mod M. AC is congruent to BD mod M. That is what it means. AC minus BD is divisible by M. This is what we proved. And that is what the second property is saying, is it not? That AC minus BD is congruent, so is divisible by M. AC minus BD is divisible by M. That is what the second property is saying. So that is what we have proved here. Any questions?
No, miss.
Okay, very good. In that case, I want you guys to think about how to prove this, okay? This is not going to be marked, obviously. There's no score here. So please try to come up with a proof on your own instead of taking any help from Google or the book or whatever. And I can tell you that all the concepts that we have learned so far, you can use those, just those, to prove this specific property, okay? So give it a try and get back to me at the start of the next session that how is it that you can prove this, okay? যে same যে methods গুলো use করেছি ওগুলো চিন্তা করবা যে what does it mean first of all to say this? It means that a plus c minus b plus d, that is a plus c minus b minus d is divisible by m, okay? And then think about how we can get there, right? So we'll discuss that.
তো ওখান থেকে তো সিম্পলিফাই করেই চলে আসবে, রাইট?
Yeah, I mean, so think about that. Think about that, how we can use the existing properties in order to prove this. And we'll discuss that at the start of the next session since we are already at 12:21, which is the end. Okay, so I'll stop the recording here unless there is any